So welcome everybody to this Next Generation Liquefaction webinar by Professor Tariq Abdoun. Really want to thank Tariq for accepting our invitation to present here. So what we'll do is Kristen will introduce the speaker, we'll hear the seminar, and then we'll have some time for discussion at the end. So I'll just say by way, before we go to the introduction, that the subject of this webinar is something we're very interested in for the NGL project, which is overburden effects on liquefaction, and Tariq's done a lot of important work in that area, along with studying the effects of partial drainage through centrifuge modeling. And so very relevant topic, and we're looking forward to learning about the work they've done, and there's also ongoing work. So with that, Kristen, go ahead and please do the introduction.
Perfect. All right. So Professor Tariq Abdoun is the Thomas Iovino Chaired Professor at Rensselaer Polytechnic Institute and a global professor in civil and urban engineering at New York University in Abu Dhabi. He earned his master's and PhD degrees from RPI as well. He is the director of the RPI Center for Geocentrifuge for Infrastructure Simulation and Resilience, and his primary research interests are geotechnical centrifuge modeling, soil structure interaction, soil remediation, remote field sensing, modeling of blast loading, and offshore systems. So as you heard, he'll be giving a talk today on a topic very relevant to our work in the NGL project. So Tariq, go ahead and take it away.
Thank you, John and Kristen, for the introduction. Hello, everybody. I'll start by sharing my slides. Let me do this right. Kristen, can you see my slides?
Yes, I can see them.
Okay. So thank you very much for inviting me here. Today I'll be talking about a research topic we have been working on in the last few years. It's the effect of field drainage on seismic liquefaction development and K-sigma under high overburden pressure. Before I start, I would like to acknowledge and thank my colleagues who worked with me closely on that work, Professor Ricardo Dobry and Professor Walid Stakili, as well as Dr. Min, who did most of this work, experimental work, as part of her PhD. Also, this work is in collaboration with the GeoComp team, which is led by Dr. Alan Marr, and we'll be talking about some of the contribution and work, small-scale testing we did over there as well. And also thank NSF and NYU for co-funding the research I'll be talking about today. I'll be briefly going over the research. This work has been going for the last 4 or 5 years. There is 4 journal publication which covers most of the topics. So if anybody is interested in more details of what I'll talk about, this is 4 journal publication, all of them in NSCE, and there is a 5th one currently in preparation, which will be coming soon. This is the outline of the presentation. I'll start with a brief background on what was the motivation. I'll do that very quickly because everybody here is very familiar with the topic. As John mentioned, this is something of interest to us as a community. So I'll be giving just a brief introduction. Then I'll start talking about our experimental work, which includes both single drainage and double drainage models. And see and analyze this data to get some insight on the values or factor of K-sigma based on the centrifuge results, as well as the soil properties, how they change. This coefficient of consolidation and compressibility depend on the confining pressure as you go. And finally, I'll be presenting some numerical simulation, which we ran using FLAX3D to kind of try to get more in depth and evaluate also the FLAX3D, which is commonly used in practice to estimate the response of liquefaction, both under low and high confining pressure. And finally, some conclusion and talk about our plan for continuing this work. So going to the quick background, how we evaluate liquefaction, everybody's familiar with this. It's basically using what we call liquefaction charts. Liquefaction charts can be based on shear wave velocity or CPT. More and more we are going to using in practice the CPT-based charts for very good reasons. But basically, both have the same concept. You are looking at what we call a cyclic stress ratio for the soil and compare that with the CRR, which is a cyclic resistance ratio curve. You have a curve which separates liquefaction from no liquefaction condition. You calculate your CSR. If it's above the curve, then that's an indication which is higher than CRR. That's indication that the soil or liquefaction is predicted, is going to be triggered. That's the basis for using the chart. These charts have served us very well in practice. The only challenge with, or the main challenge with this chart is basically they are more or less validated for conditions of shallow condition, which is typically less than 1 atmosphere. There's few points which between 1 and 2, but in general, the data or the case histories which are compiled to develop this chart are all lower than 1 atmosphere. But we have the challenge of, we have cases and conditions where the soil condition might be in the free field less than 1 atmosphere or around 1 atmosphere, but for the same soil, for a case like this, high dam, if you calculate the confining stress, it's about 8 atmosphere or higher. So how can we evaluate the liquefaction potential, and are the same charts valid or not? There's a lot of work is being done on that, and that was a question or interest of the last meeting with the National Academic Committee, looking into this, and they were looking for insight on how we can use this and the validity of this curve, liquefaction chart curve at high confining stress. There is recommendations for how to use this chart. It's basically looking at the current curve, multiply that curve with a certain correction factor, which we call K sigma coefficient. Typically, right now, the K sigma coefficient is based on small scale testing, and the recommendation for K sigma is usually less than 1, which means that the curve for CRR for 6 atmosphere is a lower curve, which means the soil is weaker and have higher potential for liquefaction at high confining stress. There is 2 typical recommendations for this correction factor, K sigma, based on Youde et al. 2001, or the more recent work by Idris and Poulanger 2008. Both give different factors at different conditions of soil. If we take one as an example to get a feel for it, so this is the curve for relative density of 60% relative density. If we look at something at 8 atmosphere, you will be getting K sigma, as I said, less than 1. Ranges between 0.5 to 0.85, depend which method you are using. So as you can see, there is a lot of variation between the 2 methods. Also, as I mentioned before, there is really not case history in the field to do it. So it's all based on undrained small sample tests, which what's available for us to use, and then no field cases. So this is mainly was the motivation for this study, to get this study started. We wanted to conduct centrifuge tests in this high range of confining stress to provide some field cases or case history to kind of validate this method and understand more in depth the behavior of the soil under this condition. So we're really looking behind what's the physics behind the phenomena as we liquefy and as we shake the soil and try to trigger liquefaction. So centrifuge testing or simulation is very good in this kind of studies because it gives a lot of insight on the physical behavior. So we conducted a series of centrifuge tests. I'll start discussing the single drainage type of test. So as we said, we are looking both at comparing the behavior at low confining stress and high confining stress. So our work is mainly looking at doing tests at 1 atmosphere and 6 atmosphere. This is the setup. It's basically simulating a 5-meter prototype in the field. It consists of a sand layer topped with a coarse sand layer, and on top of that, granule lead shot. So it's basically particles made out of lead, so it's kind of heavier to help with increasing the confinement, but it's the same size of sand particles. So it's granule material behaves similar to soil. We did 2 setups, one at 1 atmosphere, and the second one here on the right is for 6 atmosphere. Both have the same prototype depth of about 5 meters of liquefiable soil. We vary the soil properties from 45% relative density to 80% relative density. So we see the loose and dense sand. It's heavily instrumented, accelerometers, pore pressures, bender elements to get the categorize the soil, as well as LVTs. These models were built in the laminar container to provide the shear beam behavior and reduce the boundary effect. We are looking into triggering of liquefaction. So we designed this model to basically reach high pore water pressure, but don't trigger full liquefaction. So we were taking triggering or targeting RUs in the range of 0.8 to 0.9 to kind of be able to calculate our K sigma values and see the development or the triggering of liquefaction. So this is a table of the first series of tests I'll talk about. All of them single drainage. As you can see here, it's only allowed to drain upwards. It's the boundary at the bottom is impervious. So you have 4 tests. The name of the test explains it. So 45 is the relative density of the test. 1 is a confining stress, which is 1 atmosphere. 6 is the 6 atmospheres. And the second set of tests is 80% relative density, again, 1 atmosphere and 6 atmosphere. The confining pressure is measured at the center of the layer, so it might vary a little bit as you go deeper or higher, but at the middle of the layer where we focus on everything we are doing is where we are measuring this value. And the relative density we're talking about is after spin up. So this is really at the high confining stress. This is the values of relative densities we have. So if we look, this is the input motion. If you look at the bottom of the chart, in my presentation, all the black curves, this is for the 1 atmosphere. The red one is for the 6 atmosphere. So when we are doing comparison, you can know the color code for it. So as you can see, the bottom is the input motion. As I said, we are targeting a high RU of 0.8 or 0.9. And as you can see, the shaking input at 1 atmosphere for the 45, which was, if I believe, it's about 0.1 G. It was much higher. It's about 0.3 or 0.35 G for the 6 atmosphere. And you can see how the acceleration propagated and a soil or liquefaction develops or reach the soil soften, you can see the de-amplification of the acceleration. This is a pore pressure buildup, looking from the bottom going upward to in the liquefiable layer. As we said, we are targeting about 0.8 or 0.9, so this is about 0.8 or 0.85 measured at the bottom of both layers. So both of them reach the high value of RU we are targeting. And you can see as you go at middle depth, the 1 atmosphere maintains a high pore pressure buildup, while the 6 atmosphere start immediately dissipating or couldn't even build up enough pore pressure in it. And again, it continues with depth. So this is basically 0.8 or so at the bottom, and at the top about 0.4 RU. And for the 6 atmosphere, it's again 0.8 at the bottom and about 0.1 near the top. So immediately from this result, we start seeing the impact or the effect of drainage. There was kind of indication of it, so we start looking in depth more in this, so which would be clearer if we look at the isochrones of the pore pressure buildup. What you look at the left-hand side, this is the 1 atmosphere test, and the solid black line here is a liquefaction line, and you can see the 1 atmosphere almost liquefied or reached the high values of RU we are targeting till the range of about 2 meters. So from 2 to 5 meters, it's almost fully liquefied or reached liquefaction, approaching liquefaction, which is about 3 meters. If you look at the high atmosphere one, 6 atmosphere, it's only at the bottom and it's immediately dropping rapidly. And no matter, and you can see the gradient for the pore pressure in this case. So if we look at the gradient, so as I said, it increases with depth in both cases. The maximum was measured at the bottom, but what's interesting for us is really the gradient of that isochrone. So if we look at the hydraulic gradient, which is the slope of this isochrone, you can see that the slope is much higher in the 6 atmosphere, and the gradient is 1 over the slope. So the higher the slope, the following Darcy's law, this means more drainage is occurring during during the shaking of the model. So that was the first or the second indication that flow is moving from the bottom up during shaking for our test. We start looking into the results and comparing it with the small scale testing, which we have been doing with our colleagues in GEOCOMP. So we ran a series of stress and strain control tests at GEOCOMP using the same soil, and we did it for the relative density which we are using in the centrifuge, where in this case we are comparing with the 45. So we use the same sand batch and we did the testing over there. We did the confining stress both at 1 atmosphere and 6 atmosphere, and again we targeted the same RU values so that we can compare the results with both cases. And the centrifuge is all the tests were done initially at the beginning at GEOCOMP were done undrained condition, which is the typical way is being done in practice. If we compare the behavior between both tests, the centrifuge and the triaxial test, this is the isochrone I just showed you for the 6 atmosphere test. If you look at the buildup of pore pressure at the bottom of the layer here, which is the solid line, in 10 cycles, we built about 0.8 RU. And if we look at the same soil being tested with the triaxial, which is the dotted line here, you can see it built exactly the same kind of behavior in 10 cycles in the undrained test. So this is kind of confirmed that's more or less at the bottom of the layer in our model. It was really behaving closer to undrained because, again, the boundary is impermeable. If we do the same comparison near the surface, where near the permeable boundary, again, the solid line is what you see in the centrifuge. The dotted line is what you see in the undrained triaxial test. Very different behavior than what we observed either in the bottom or in the undrained behavior. So it's obviously it's draining much faster. It can build up much of RU during the shaking because it's draining faster than you are building pore pressure. Another observation, looking at the isochrones, again, as I said, in the 1 atmosphere, the build-up of high pore pressure is a zone, so it's about 2 meters or 2.5 meters of high pore pressure. In the 6 atmosphere, it's almost a point near the impermeable boundary, and it's very, very a steep slope. Is basically draining quickly or highly. So again, observation from this, it's harder to liquefy at the 6 atmosphere. That's based on the observation we had from the centrifuge. And even if you reach liquefaction or close to liquefaction, the zone of this high RU is much thinner than expected or than what you get in a much shallower layer. We took that further and we start looking more into the effect of the drainage. So we did repeated this test, but now with double drainage, allowing now drainage to occur both in the bottom and at the top. So we repeated the same models I showed you earlier, again, 1 atmosphere and 6 atmosphere, but we added a drainage boundary at the bottom. So now the soil can drain upward and downward during shaking. And we repeated the same test, again, the same kind of conditions, the same confining stress. And we started by repeating the test with the same input motion. The same input motion which generated almost liquefaction in the single drainage. We use the same input as a start to see if we are going to get the same buildup or the drainage, change in drainage will make a difference. And this is the first comparison. This is a 45% relative density at 1 atmosphere. What you see on the left is the single drainage. SD stands for single drainage. DD is double drainage. So as you can see, this is the test I presented before. As soon as you have drainage, again, now it affected significantly the bottom of the layer as it starts showing some potential drainage, but still you built a significant amount of pore pressure during shaking, not as high as before, but certainly a significant amount of pore pressure buildup. If we look at the 6 atmosphere, for the same level of shaking, now with double drainage, initially you were reaching values of about 500 kPa. Here you're hardly reaching 100 kPa. So almost no buildup of pore pressure because of the double drainage effect. And significant effect for the drainage when you get into the high confining stress, more significant or more apparent than what we saw in the single drainage. We repeated this test, but I'm not showing this here to basically reach the high confining stress, but we had to put much more input motion to be able to build that so that we can calculate our K sigma. But for the sake of time here, I'm not presenting that, but we repeated the same test, again, a new version model, and put the higher input motion, and we were able to capture high values of RU, but as I said, it required higher shaking input. So we used this data from all 8 tests to kind of start looking into the values of K sigma based on the observation for the centrifuge, which simulates more or less the condition of the field condition. So typically to calculate K sigma, just to refresh everybody's mind, basically you calculate the stress ratio, which is the stress with time over the confining stress effective. And if you have the stress ratio histories, you can calculate your CSR, both for the 1 atmosphere and 6 atmosphere. So it's a direct calculation. And the ratio of this CSR at 6 atmosphere and 1 atmosphere will give you the K sigma you have. So we use that to calculate K sigma for the centrifuge test. This is an example of the stress ratios measured in our test. Again, remind you the black lines or the black curve is a 1 atmosphere. So this is for the 80% relative density. And for the 6 atmosphere is a red curve. And as you can see, the stress ratios in the 6 atmosphere are higher than the stress ratios for the 1 atmosphere, which is kind of opposite to what is being estimated based on the undrained behavior. So if we take these values, and again, we did it for the 45% and the 80% and use that to calculate the K sigma. So if you calculate K sigma, you get values which is about 1.3 and 1.5, depend on the condition you have in these. This is all for the single drainage. So it's obviously from this measurement that the higher the confining pressure, the soil is draining faster, and we'll look into why that's happening. And because the soil is draining faster, you are not building pore pressure fast enough or as fast as being estimated based on the undrained condition. So we compare these values. The blue values are what's being estimated with the current curves from state of practice. So as you can see, the values, if we look at the 45, what we get from the centrifuge is about 1.3. In the current K sigma values is about 0.7 or 0.85. We went back and calculated our what would be K sigma if we use our undrained triaxial test. So if the assumption of undrained behavior is valid, what would be K sigma? And certainly the values are very, very comparable to what's being given by Idris and Bull and Yates, about 0.85 or 0.84. For all practical purposes, is the same number. So basically, the issue is the method is correct, but is the assumption of undrained is the right assumption for high confining pressure? Based on the results of the observation, it's very valid and stands strong for the case of low confining pressure. But as soon as you go to high confining pressure, it might be a very conservative assumption. To assume the soil is still undrained is conservative, is not utilizing the soil behavior to the fullest. So certainly the soil is draining, and if it's draining, it's reducing the potential for liquefaction. That's why K sigma being measured is higher than 1. So we use that as an exercise to look how that would impact the prediction of if the soil will liquefy or not in our test. It's, again, centrifuge test is like a case study. So we use the CSR we have for our centrifuge test at 6 atmosphere and use that or multiply that with, divide that with the K sigma values, both from the chart as well as what we calculated based on the centrifuge. So if we use a chart, that would estimate that the test we did would liquefy. And if you recall, we never liquefied. We reached high RU, but we never liquefied. If we use measured K sigma, it will put the values for the tests we conducted is that it's not expected to liquefy, and that's really what we observed. We reached about 0.8, and actually in that case, if you recall, it reached that only at the boundary. The rest was much lower than that. So it certainly didn't liquefy in that test. So that gives you a feel how that K sigma value might make a difference in predicting if the soil is going to liquefy or not. You might be conducting remediations unnecessary in certain conditions because of underestimating the values for K sigma. This is the same table from before. We added to it the value from the double drainage. As I mentioned, we did the tests again and we reached the high RU values, and we repeated the same process, and you get RU again about 1.3 for the double drainage. So it's kind of confirms what we have been observing. The single drainage is also being shown in the double drainage. So in quick summary of what we have observed in the centrifuge test is that K sigma seems to be higher than 1 because the soil behaves more drained at high confining stresses. And also the other interesting thing is that K sigma decreases with relative density. That's the same trend with the charts from the state of practice show. So that confirms that trend. So if the soil is behaving more partially drained or and so certainly the stiffness of the soil or the coefficient of consolidation would play a very major factor. So we start looking into what values we have for the coefficient of consolidation. So because if we are looking at CV, the values for CV which we calculate from the physical test or the centrifuge should be consistent with the behavior if the soil is draining or not draining. If that same trend have to be shown in the centrifuge to give credibility of the results. So we went to the basic soil mechanics and tried to see if things adds up and all the puzzle pieces fit together. So we use the data from the centrifuge to calculate the CV using the consolidation theory. What you have here is on the right-hand side is the dissipation curve, and we use that to get the time for the soil to consolidate, use that to calculate our CV value. If you have CV, you can calculate your M prime, which is a volumetric stiffness, and you can calculate that both for the 1 atmosphere and 6 atmosphere, and we did that. And based on basic soil mechanics for sands, it's supposed to be around the value of square root of the change in confining stress. So for our case, for 6 atmosphere, the change in CV or M prime between 1 atmosphere and 6 atmosphere should be about 2.5 times roughly. And we did our calculation for our CV and M values in the centrifuge. And for all the tests, they varied somewhere between 2.4 to 3.2 or 3.4. So as an average, it's about 2.7, which is very, very comparable to the value we get from basic soil mechanics. And that's explained that the higher the stiffness of the soil, the easier for it or faster for it to drain. And that's why the soil at high confining pressure, it's the same soil, the same relative density, but it's much more stiffer. That's why it drains much faster. The other interesting, because we were interested in using FLAC for the simulation, and that's what most people use in practice to do liquefaction prediction. FLAC correctly incorporates that root square rule. So actually, for the same soil, the same relative density, the value for CV or M prime is changed by the square root, which is already built in the code, so you don't need to change or do any correction. It takes that into account, and we'll see that when we start looking at some of the simulation which was done. This is also a plot of the volumetric stiffness for our test, and you can see for the same soil at 1 atmosphere, the stiffness curve, and at 6 atmosphere, it's very clear how the much more stiffer. It's, as I said, if you take the comparison of these 2 points, it's about 2.5 or 2.7 the value, which again verify what you expect for typical soil mechanics. We wanted to also develop a way for people or practitioners to use this method or utilize or be able to estimate properly the stiffness of their sand. No need to every time to go do a centrifuge test. So the GEOCOMP team is leading an effort to try to develop a new test, triaxial sand compressibility test, to be able to predict this value. This is a result from this new procedure they are developing, where they are running the triaxial test drained, and after they reach the high RU, open the drains and let it consolidate while they are measuring the change in stiffness of the soil or the volumetric change of the soil, and can estimate what the value of the volumetric stiffness. So that's, again, work was led by the GEOCOMP team, but I just want to show that we are also looking into trying to provide tools for people to, or practitioners to be able to use this information. It doesn't need to go through a complicated centrifuge test every time, but you could be able to get the same information about the soil using a triaxial test, but slightly modified how you run it. So looking now into the numerical simulation, as I said, we used FLAC 3D. We wanted to simulate our test and see how current numerical method would be able to simulate properly the behavior of our centrifuge test. So we started with a single drainage test, and that's what I'll talk about here today. So we did 1D shear beam soil column simulation for the 4 tests, which are single drainage. both at 1 atmosphere and 6 atmosphere, 45 and 80%. We used the cycle triaxial test along with the centrifuge data to calibrate the flag code to start with. We ran the simulation, both fully coupled effective stress analysis and no flow analysis. So fully coupled is basically, in simple terms, you are allowing for the water to flow during the shaking, during the simulation. No flow is basically you are running it undrained. Typically, people run the no flow because it's much faster, and we'll see how that assumption works both for the low confining and high confining stress. So just to clarify what we did, this is a comparison between the simulation at 1 atmosphere. The blue is the experiment, and the dotted black line is a coupled simulation using FLAC. This one is not a prediction. This is basically the first model we use to calibrate. So this is class C. We're basically using the experiment to calibrate our FLAC model. Started with what's recommended by FLAC team, and we did few changes to few parameters. And these parameters are kept constant from now on. So for the other 3 tests, we didn't change anything. As I said, FLAC itself accounts for the change in confining stress, so we didn't even need to change the model of stiffness, the M prime or CV. And the same thing for the 80% relative density. All what we did is change the relative density, and we didn't change any other parameters. So if we look at the comparison, so more or less for 6 atmosphere, it's really a prediction. So this is a comparison between the centrifuge measurement and the coupled simulation using 3D FLAC analysis. The comparison looks pretty good. We then ran the simulation again, same parameters, but now we didn't allow for the flow to occur. We did the non-flow. And as you can see, this is the comparison you get. For the 1 atmosphere, it's pretty good. It looks, the comparison seems to be decent, very small variation near the surface. If you look at the 6 atmosphere, the no flow, you can see it's way over predicts near the surface. It under predicts at the bottom, only close to the values near the middle. If we go to the next level of testing, which is the 80% relative density, we repeated the same exercise. This is again the full flow comparison. As I said, we didn't change anything. The only thing we change is go from 45 to 80% relative density and keep all the other parameters the same. And you can see the comparison looks, in my opinion, looks very good between both the coupled and experiment. So really, we have the tools, seems to be giving the right values if we allow to run the proper simulation. If we do it again, and now we are closing the flow, very good comparison at 1 atmosphere. And I think that's what we have been guided by, because this is where we have a lot of case histories, and people from practice have seen that if you run it coupled or no flow for the low atmosphere, it seems to be giving pretty decent values. That's where we didn't have much experience, but it looks like the values are very different when you go to high atmosphere. It makes a difference if you run coupled or no flow simulation. This would be more clearer if we look at the profiles. This is the profiles for 1 atmosphere, both for the 45 and 80%. This is all 3 of them. The blue is the experiment, and the black and red are the 2 simulations, with flow or no flow. And you can see the experiment is bounded by both of them. For all practical reasons, both of them seem to be giving a very decent prediction. When we go to the high confining stress, you can see the predictions with the no flow is very, very different. Misses the profile. It's overestimates and underestimates in different condition. If you go to the high relative density, again, it assumes the soil have reached close to full liquefaction for the full depth, while in reality, it only builds some high pressure only at the bottom or near the boundary. This difference is even more significant when you get into the double drainage. This is a single drainage. So at least from what we observe up to now, and this is a work in progress right now, it looks like it's a big difference if you run the simulations, no flow or coupled flow in reality. So some observation and conclusion and some discussion about future work which we are planning for. So we developed a new centrifuge technique to study liquefaction at high overburden pressure, and it seems to be providing some useful insights on the behavior. Clean sand at high sigma V is less compressible, it's more stiff, and that's why it drains faster during shaking than what you observe in the behavior at low atmosphere, 1 atmosphere or lower. Centrifuge results confirm that undrained behavior for low overburden pressure. So as we showed that, yes, based on the results or the experiments we see, what we have believed that assuming undrained behavior for low confinement seems to be valid, but indicates more drained behavior of the soil is being observed at high overburden pressure. And as I said, we have seen that from the experiment, from the comparison between the centrifuge as well as undrained triaxial, from the basic soil mechanics of how the soil compressibility or stiffness is changing with the increase in confining stress. For partially drained field condition, field K sigma is usually, or being measured, is higher than 1. That means it's harder to liquefy at high sigma V rather than easier. So the assumption that K sigma for high confinement is less than 1 means that it's easier to liquefy. What we have been observing, or what's indicated by the centrifuge result, that because of the drainage occurring, K sigma is actually higher than 1. And even if liquefaction occurs, the zone is much thinner in the under high confining stress. So I know also in practice it's important how big of that layer. So even the thickness of that layer, it's not the full layer, it's typically a small zone because things seem to be draining. As we mentioned, the M prime and CV are proportional to the change, square root of the change in confining stress. For those partial drain field condition, that means K sigma increases instead of decreases with the increase of sigma V. Finally, as I said, this is a project which is a work in progress. We have been working for some time now on it, but we are halfway in our work. The plan is to do additional centrifuge tests. We are starting to do silty sand. So we want to validate or look at and learn the behavior also in the condition of silty sand, and also varying the thickness of the layer or the liquefiable layer. We are planning a numerical study to try to widen the range of data for understanding the behavior. So we'll use models, the numerical models which are calibrated with our centrifuge tests, the 8 tests we have, and broaden the range by looking at how the behavior can be predicted with this numerical simulation. Then finally, we are hoping to provide guidelines on when the K sigma in the field would be assumed more than 1, and basically the validity of the chart, when we should be assuming that the CRR chart need to be reduced or need to be kept as it is. And again, we are in the progress of learning more, but the indication we have up to now seems that CRR doesn't need to be reduced, at least in the cases we have looked at. With this, thank you very much for listening, and look forward to any questions.
All right, thank you. Thank you very much for that wonderful presentation. I'll remind the attendees that you are welcome to use the raise hand feature. You should be able to hover over your name and raise your hand if you have a question, or if you have a question you'd like to type into the Q&A panel, that is also an option. I see there's something in the Q&A panel from Scott Brandenburg. So we can answer that question first, and as the questions come in, we can invite different attendees to unmute themselves. All right, so Scott, I will actually give you a chance to unmute if you'd like to ask your question. All right, so
first, Chris, can you help me read what the questions are? Because for some reason,
sure.
The panel is very small. I can't see what's written. Oh, okay, now I was able to extend it. Okay.
Yeah, if you can read it, go ahead. But if you'd like, I can read it out for you.
So the first question, and again, Ricardo is here and will lead. Please feel free to jump in if you would like to add anything. They are also part of that study, so anytime you have the access to unmute and answer as well. So I'll start by the first question from Scott. He's asking if the effect of the drainage should be included in K-sigma or through a separate analysis that probably accounts for permeability and drainage. We use the K-sigma because it's what's being used in the practice. A lot of people, and that's why sometimes we refer to it as field K-sigma, because people are used, or that K-sigma is based on undrained cyclic tests. So either you include it in K-sigma as a calculation or do it separate analysis. Bottom line, that the combined effect should be shown in the analysis or calculation. So the effect of the drainage should be accounted for. We picked the K-sigma because that's what people are familiar with in practice and it would be relevant to them. But if there is other approaches to basically have a K-sigma parameter and another parameter for the permeability and the drainage, and the sum of these two parameters would be above 1, that's fine too. But that was the approach we started with. Okay.
May I say something?
Go ahead, Ricardo.
Yes. In fact, there have been a lot of discussion, some of this from the reviewers of the papers we have submitted, about the definition of K-sigma. And it's true that until now, K-sigma has always been defined on the basis of undrained tests, because that's the only thing we have. And some people like it and think that K-sigma should be a material property, an undrained material property, uncontaminated by drainage considerations. On the other hand, in practice, K-sigma is used to correct the charts, which include all kinds of things which are not necessarily undrained and may include drainage. And that's the position that the National Academies in the workshop on liquefaction they had a few years ago took, that K-sigma should be investigated with field case histories if possible, if not with shaking table and centrifuge tests, including the possibility of drainage, because that's the way K-sigma is being used in practice. Thank you.
Right. So the next question, and Kristen, if I miss any questions, please help me. I'm going from the top down. Can you tell us what factors were controlling the stiffness in your soil? The soil stiffness depends on how you prepare your model, all this, the fabric of the soil, all this kind of stuff. All these methods were the same in all the tests. So the only varying parameter in our tests were basically the change in the confining stress. So the only parameter which would lead for this change in stiffness was basically spinning the soil or confining it at a higher confining stress, because everything else was remaining constant or maintained the same. The next question, was the actual void ratio after confinement the same in the 1 atmosphere and 6 atmosphere? Yes, and that's what I mentioned during the presentation, that this values we are reporting is actually after reaching the high confining stress just before shaking, and that this is our relative density values. We use the shear wave velocity and the measurement of the settlement to do corrections to kind of calculate what was the relative density or the value before we start shaking our model. Then, thank you very much. Okay. So Scott seems to agree with the answer. I'm reading. So basically, the question is asking, is there any metric you use for drainage condition in the experiment? Which fluid you use? Is it viscosity scale with the prototype? Yes, we use viscous fluid, and it's scaled with the prototype. So if we run the test at 20 G, it's 20 times the viscosity. If we run 60 G, we run it 60 times viscosity. I'm not really clear what's meant by the metric used for drainage conditions. It's basically we had 3 drainage boundary on the top and the bottom. We had geotextile at the bottom with drainage outside of the container. So it's kind of more or less very permeable compared to the soil itself. And we didn't see any back buildup in pore pressure. So the assumption of being permeable boundary in the top or the bottom, I think seems valid.
It looks like the next question in there was a question about whether there was ejecta evidence during those experiments.
We always make sure to check if we had any ejectile either within the core sand or within the lead, or any indication of soil flowing upward. We didn't. Maybe at the boundary between the core sand and the liquefiable zone, there was some mix of the two soils, but no ejectiles that you can see have penetrated through a certain point.
Thank you. I see we have 2 hands raised, so I'll pause the written questions just for a second to give some of these other participants a chance to ask live their questions. So I see Majid has a question. I'll invite Majid to unmute and ask the question.
Yeah, thank you, Tariq Abdul, for the nice presentation and the insights. So actually, I just had one query. I don't think it is related. So will there be any permeability change in the material after this input motion?
I didn't hear exactly what was changed.
So because after there will be the drainage from high pressure to along the pressure gradient. So what about the permeability change that might be happening because of the liquefaction?
It have been observed or estimated before that soil, when it liquefies, the soil permeability increases. I don't want to use the wrong numbers in top of my head, but I recall that even in numerical simulations, they tend to increase the permeability, few times more, or could be even up to 10 times increase. But again, I don't remember exactly the factor, but I have seen that, or people use this type of factors. But bottom line is, it's a value, a multiple of what you start with. And whatever you start with is you are multiplying with it. It's different than what we are looking here for. It's basically the potential for the soil to be able to have flow inside it. When you have the same soil under a low confining pressure compared to when it has high confining pressure. Because the soil under high confining pressure is much stiffer, has less voids, it's very easy for it to kind of drain soil, or less compressible. It's much easier to drain water out of it. That's based on consolidation theory.
Thank you. I also see Armin has a question, so I'm going to give him a chance to unmute as well.
Yes, good afternoon, Tarek, and thank you very much for a great presentation.
Thank you.
I think the evidence you've presented is compelling, and I think we've seen some confirmation of that in the field. I'm curious about applying this in forward analyses with the simplified method. It appears to me that the distance, let's say the drainage path of a given layer, should control whether things act in a partially drained or fully drained state. So I guess I'd be curious on thoughts about applying maybe drainage path length dependent case sigmas, if that might be a direction that we need to go.
That's a very good point, and that's one of the things we are looking into in the future work, varying the thickness of the layer, having a preferable passage for drainage. Also, we are hoping, again, if we have the resources, look also the effect of horizontal drainage. If you look at the case in the field where you're in a dam or something, drainage doesn't have to be only vertical direction. It can go towards the free field because there's less confinement there. So we are hoping with the future work, we try to vary these factors and look how that impacts. The indication we see up to now is that this also might be helping to increase the value of K sigma or the effect of the drainage effect.
Indeed, thanks.
So we're at the end of the hour, but if you'd like to take a few more questions, we could do so. Or I have written these questions down, and we can definitely invite others with questions to contact you directly. Is that right, Tariq?
I can take a couple of more, and then the rest people can send it to me. I'll be glad to answer, or even if they want to chat, we can always log in Zoom, WebEx, and chat. But I can take a couple of more.
All right. Let me first ask if any of the panelists had a question that they wanted to ask live before we wrap up. So John Stamatikos, John Stewart, or Steve, any questions you had?
Well, I'll just ask one. So thank you very much for the presentation and the very interesting results that your team has obtained. Clearly, the drainage effect is going to be extremely dependent, not only the drainage path length, as Armin pointed out, but also on the conditions at the boundaries of the layer. Is that a free draining layer, as it was in your tests, or is that maybe something that's a little bit siltier, or maybe even clayey? So there's all sorts of complexities that get involved in how free draining a sand layer is. And so I guess my question is, are you considering running centrifuge tests in which you would look at those situations where it's not free draining? And my guess is you would get very different K sigmas, which I do think calls into question whether we should really be calling this K sigma, or should you be calling this something else that reflects drainage and all of the complexities that go with drainage that, in fact, we as geotechnical engineers do know how to model. We have frameworks for that. But I guess the direct question is, have you, or are you considering in your future work a case where the drainage would be impeded relative to what you've already tested?
Yes, we understand very well that the results depend on the drainage, and that's why we are looking at both ends. We have been doing the single drain, double drain, and the next step we are looking into the ones which basically no drainage or not free drainage. But again, there would be, could be a water interlayer or whatever. But again, this is things which we have to look into it, and the results of the centrifuge is what we learn from. Also, we are looking into things which is less permeable, like silty sand. That's why we're also looking into getting into this condition. If we call it K sigma or something else, as I said, we picked what people have been familiar with, but it can be approached different ways. If the study shows that, yeah, it's more complicated and things can vary significantly depending on the boundary condition, then I agree with you. Maybe we want to separate this and have another factor depending on the boundary condition. If we find that even with less permeable boundaries, still we are getting the same effect because the stiffness is so different, then maybe it's not. So I think we should continue the study, and based on what we get, we decide how we should proceed. But we are certainly trying to look at all this.
Okay, great. Thank you.
May I add something?
Mm-hmm.
I don't think we should get caught into a discussion of semantics, K sigma or not K sigma. What the practitioner wants to know if the liquefaction charge, which is valid for 1 atmosphere, has to be lower or not, or it can be used at high pressure without modification, and by how much to lower it. Any way we answer that question, it really doesn't matter how we do it. I don't think we should get caught into what should be K sigma. We should come back to the question the practitioner is interested in. Thank you.
Thank you, Ricardo.
If you have time for another, I'm making a list. There are quite a few questions coming in, but I have one here that was asking how it was ensured that hydraulic conductivity was consistent between 1 and 6 atmospheres, and could the different modeled layer thicknesses affect drainage differently when compared to the 5-meter prototype thickness? That may have already been answered, but I wanted to make sure we covered that.
It's actually being covered. Basically, when you conduct a centrifuge test, you keep all the preparation procedures the same to kind of ensure no variation between both. We had, what you see is there is a successful test. There is a lot of preparation tests which done to learn, if I want to reach a certain relative density at a certain confining stress, I need to build it at a lesser value and so on. So there was a lot of preparation and testing, examination to make sure things are consistent between all the models so that we don't reach any wrong conclusion. So hopefully that addressed that question.
Thank you. I have written down a couple more, but I think I will pass those on to you so that you can contact these individuals directly.
Sure.
If you have, I think that's everything we have time for. Thanks, Tariq.
Yeah. Thank you, everybody, and thank you for inviting me and for being here too. And look forward to continue working with you in this project.
Thank you. As do we. Thank you again.
Yeah.
All right,
Thank you, Tariq.
Bye, everyone. Bye.
Bye-bye.